So my name is Vincent Pelgrims. I'm currently working at the Institute of Astrophysics in Crete, Greece. And for the last 2 years and a half, I've been working for the Pasiphae project. And I've been asked to present the project today. And Duncan asked me to put Pasiphae in the context of galactic science. But so I will do so, but I would like you first to remember that Pasiphae, the main goal of Pasiphae is actually to go through the veil of dust that is the main annoyance for CMB polarization science. So the goal of Pasiphae is indeed actually to help studying and characterizing the galactic foregrounds. As we all know, I think, is that the galaxy is made of a lot of things like relativistic electrons and dust grains that do interact with the ambient magnetic field in the galaxy, and so produce polarized emission that dominates the CMB frequencies. At low frequencies, we have the synchrotron, and at high frequencies, we have the thermal dust. And as is can be sketched by this cartoon here, polarized emission, both synchrotron and dust emission, they do trace the plane of sky magnetic field orientation, since both are perpendicular to the line of sight. And this actually is great for galactic science, because that means that from CMB data, one can study galactic foregrounds and indeed extract some information about the magnetized ISM inside our galaxy. And this is, yeah, Susan and Brandon have largely talked about that before, but the whole point then is to take such kind of map that you can see here, and to extract parameters or physics from those full sky map of polarization. Here it's blank, of course. And in that kind of work, of course, one has to remember that this map is a view of the plane of sky component of the magnetic field that has been integrated along the line of sight and weighted by the matter density, either the cosmic rays electrons if we look at synchrotron maps, or the dust grain if we look at thermal dust emissions, so high frequencies. And the fact that we can extract some physical information or some properties of the magnetized galaxy, I think, can be well illustrated by this plot from WMAP paper, this wonderful paper by Page et al., where they were modeling the data using, well, constraining a three-dimensional model of both galactic magnetic fields and matter density distribution. And as you can see here on this plot, here we have the position angle in the in K-band, so about 30 gigahertz. And this is the position angle recovered by the best fit model that they have. So by putting constraints, actual constraints on the parametric model. So this kind of opened up the way of constraining our knowledge or understanding of the magnetized galaxy by using CMB data, I would say. And of course, many people have went down to this road using synchrotron data, but this is also feasible with dust data. But in this kind of business, one quickly realized that we are a bit limited in terms of putting some meaningful constraints on the parametric model. First, because the ISM is turbulent by nature, which means that if one came up with a nice 3D parametric model, it will have to put some stochastic model in it, which then in each step of the MCMC sampling, for instance, it will have to make vary this stochastic model, and that's quickly start to be computationally demanding. And obviously then start to have lots of degeneracies between the degree or the amplitude of the stochastic component in your modeling, and all the things that you cannot really probe or model using your simple parametric model. So there are degeneracies. And most of those degeneracies also come from the fact that the observables, so the Stokes parameters, Q and U, basically, they are, well, line of sight integrated right? And so all the information is lost, all the third dimension along the line of sight is lost while imprinted in the data. And this, as we know, causes line of sight depolarization if the magnetic field is, changing orientation along the line of sight, and which, if we had SED variations, like dust SED variation, for example, then we have frequency decorrelation, which we know we have across the sky and through the sky towards complex lines of sight. And this is a very critical point for a template extrapolation of foregrounds in the context of CMB. So the fact that we are dealing with this 2D view of the magnetized ISM using Stokes parameters are both annoying for CMB science because of this frequency decorrelation and line of sight depolarization, but it's also annoying for the galactic science because, well, we are missing one dimension. So one of the dream maybe would be to be able to invert this line of sight integration, this line of sight integration process. And by saying so, I mean slicing the emissions really in Stokes Q and U, slicing in terms of distance. And this is where starlight polarization may help a lot, because indeed, we know that starlight polarization traces the plane of sky magnetic field and the dust in the ISM, and this is well known since almost, well, more than 70 years ago now. And this is the only way to explain those large-scale features that you can see on the map here, where we see polarization vectors of all the stars in a catalog of L's in 2000. And the very important point is that the dust that induced the polarization to the starlight is actually the same dust that is observed in emission in the microwave frequency. So at frequencies relevant for the CMB. And this can be sketched by this cartoon here, where we have background stars which emit light that is unpolarized. And when that light passes through a cloud of dust, where all the dust grains they are spinning with their minor axis aligned with the magnetic field, it will absorb all the electric fields that are perpendicular to the magnetic field. And so the observed polarization of the light of the stars will be like, parallel to the plane of sky magnetic field. While in emission, due to the rotation of the spherical dust grain, then we have the emission that is perpendicularly polarized to the magnetic field line, as I said earlier. So from this cartoon and theory, we do expect actually that both dust emission and dust in absorption through the study of starlight polarization is very well correlated. And this is actually the fact, as it has been demonstrated by the Planck collaboration here, and that can be illustrated with this plot where we have on the y-axis the Stokes Q and U as observed at 353 gigahertz, so in dust emission, and the Stokes parameters in absorption seen just from the stars. And we see that we have a very stringent correlation between the two, which means that there is a conversion factor between dust in absorption and dust in emission. And this is very important because that means that starlight polarization can be used well, it is predictive of the dust in emission. And the very important thing with starlight and polarization and stars in general is that we can probe the distance of the stars, which means that we have a way to localize along the line of sight where is the emitting region of the dust here in particular. And with a student here at the university, we kind of already exploit this this phenomenological thing to demonstrate in a way that at high galactic latitude, the polarization sky as seen by Planck is actually dominated by a dusty and magnetized structures, which is located at at a distance of between 200 and 300 parsec, which corresponds actually to the edge of the local bubble, which is a well-known structures in the local ISM. And based on this observational fact, one can then start making a good choice in the modeling of the magnetic field, but also in the modeling of the foregrounds, as we did in that paper here, where we proceed to an actual reconstruction of the 3D shape of the local bubble using a three-dimensional dust extinction map, and then where we have fit the parameters of the magnetic field, constrain the parameters of the magnetic field through a fit of Q and U in of dust emission. Good. Starlight and coupled with distance can help us making appropriate choice in the modeling, but ultimately this is not where we want to go. Where we want to go is to use starlight polarization and distance to proceed to an actual inversion of the plane of sky magnetic field and the dust. So to end up with an actual 3D maps of the magnetized dusty ISM. And this in principle could be feasible if we have a sufficiently high number of stars, polarization measurements of stars along one line of sight, because the polarization that is induced to the stars is actually additive from the cloud, which means that all the cloud that are in foregrounds, they leave their imprint on the polarization of the stars. So if you have a sufficiently large number of measurements, you can invert these equations easily and constrains the column density of clouds and the position angle of the magnetic field in each cloud. This has been demonstrated to be feasible for one particular line of sight in Panopoulou et al. 2019, where in this particular region in black here, they have been able to show that the ISM is made of two clouds at different distances, and the magnetic field is in different orientations. So this was done by considering the polarization degree and polarization angle as a function of distance, and a careful analysis of this data set allowed them to recover the column density and the plane of sky position angle of the magnetic field, which actually corresponds to some features as seen in H1 emission here. This kind of analysis is actually now being performed even by different teams. So it shows that it is feasible. However, to be helpful for CMB foregrounds, we don't want to do that for only 1 or 2 pixels on the sky, but we would like to do so for a very large area on the sky. And currently, this is not feasible because the current status of polarization catalog is well, there is not enough stars, as it can be shown from this histogram here, where we have as a function of galactic latitude the number of stars per square degree, and we see that we have almost no stars, no data point at high galactic latitude. This can also be observed in this 10 by 10 degree field, where all the red segments show the currently available starlight polarization measurements. And this is where Pasiphae will come in, because Pasiphae is meant to fill the gap. And this is what we expect to be able to measure or to deliver with Pasiphae. So I can go back and forth. We do expect to have such an increase of starlight polarization measurements. Yes. So now that I'm speaking about Pasiphae, let me introduce the collaboration. So the collaboration is spread over 5 nodes. The PI is at the Institute of Astrophysics in Greece. Then we have a node in Oslo, a node in Caltech, one in Sutherland at SAO, and one in Pune in India. And the collaboration is made of about 21 members. Among them, we are like 13 or 14 grad student and postdoc. And we are running with fundings for salaries, but also the constructions of instruments. because Pasiphae is also about the construction of two instruments, the wallops, that will be placed in the two telescopes at Skinnacas Observatory in the Northern Hemisphere and in the ACAO observatory in South Africa. So what we plan to do with those instruments mounted on those telescopes is to perform a survey of starlight optical polarization. And the survey is planned to be in two phases. The first phase that we call the shallow survey, we will scan the sky down to a SDSS error magnitude of 15, which has been proved to be deep enough so that we can map all the significant, all the clouds that contribute significantly to the polarization signal. And in 3D, this corresponds to a 1 or 2 kiloparsec distance. This first phase will take about 2.5 years of observation to cover this 2,000 square degree. And that, according to Gaia, this corresponds to a mapping of more than 4 million stars. Then when this first phase will be done, we will go into what we call the deep survey, where we will drill the sky down to a SDSS error magnitude of 16.5 in well-selected area of the sky, where the ISM look more complex or where there is an increase of interest for the science. And using this deep survey mode, we will be able to cover 1,000 square degree per year additionally. So this is the plan. And of course, first we need to have the instruments. The instruments are called WALOP, for wide area linear optical polarimeters, that have been designed especially for the Pasiphae program. This was a technical challenges because it needs to be a wide field and of course, very accurate and sensitive and with high efficiency. The reason it needs to be accurate and very sensitive is because we know that we are looking for a signal that is weak by nature. So we need to have a very high control on the systematics. The solution the engineer come with is a 4-camera one-shot polarimetric concept, which means that for each sky patch that will be observed, the light will be split in 4 different polarization states. And then from differential photometry, we will be able to recover the Stokes Q and U of each stars. This solution has some key aspect that you can read here, which is that we will, by doing this differential photometry, we will reduce the sky background by a factor of 4. And also by having these 4 images separated on different CCDs, we will have no overlap of the images, which is mandatory if we want to go very large field of view observation. This is the optical design of one of the 2 instruments, where we have the focal plane of the telescope here, then some optics to collimate the light down to the polarizer, which is made of a huge Wollaston prism of 9 by 8 centimeters. And so that creates, well, that separate the light in 4 polarization states. And the 4 polarization states are then divided along the different arms, where there are a couple of lenses to refocus all the light down to the CCDs at the end of each arms. And the CCDs will be like 4K by 4K. This is the same view of the instrument, but with its dress, and here with all the infrastructures that guarantee that all the optical elements will keep their alignment down to about 30 micrometers, which is required to have this highly accurate instrument at all inclination and azimuth of the telescope. The next challenge is the calibration of the instruments, because as I already said, we will be looking for very low signals. So we need that the instrument is calibrated in terms of Q and U Stokes parameters down to 0.1% over the full field of view. So the only way to correct for all the crosstalk that can arise in the instruments between Q and U, but also all the things the way to correct for those effects is to develop an instrument model for a non-sky calibration, and this model has been built and tested and validated based on simulation, but also based on a prototype of the WALAP in the lab. And this model instrument and all this process show that we do achieve the 0.1% accuracy over the full field of view, which is a good news, of course. And when we speak about optical polarization and calibration, of course, that means that at some point we will have to look at the sky and calibrate the 0-point polarization angle, which means that we need standards. And this is the reason why for the last couple of years, we have performed some surveys of standards, which are completed now, almost. And that means that we are now ready to be ready to be on sky. And this is well in time, since the WALAP South is scheduled for commissioning in a few months from now. And WALAP North will follow, so likely next spring here in the Northern Hemisphere. And after that, the next challenge, of course, will be to go from the starlight polarization catalog that we will hand to go for tomography, which means to go from the starlight catalog of 4 million stars to go to a cloud catalog. So placing the clouds, well, invert, put the clouds along the line of sight, put them together, and constrains the plane of sky magnetic field orientation around them. The next step will be to go from this cloud catalog to foregrounds modeling. So in multi-space, I say multi-dimensional here, because it is actually 3D, but also in terms of frequency, we can obviously model different SEDs per cloud. And this is a summary. And I just wanted to mention for the galactic science that that Pasiphae is not only a machine for CMB foreground characterization, but it's also it will have a wider impact in the area of galactic science, since we will have this actual 3D maps of the galactic magnetic field. We will be able to address some of the outstanding questions about the geometry of the magnetic field, the origin, eventually its role in shaping the galaxy. We will also likely help other area of research, like the cosmic ray propagation questions, which we will hear in the next talk. And maybe we will help answering the question from where do come from those ultra high energy cosmic rays. And also by providing millions of starlight polarization measurements, but not only, we will likely contribute to stellar astrophysics and the high energy physics. If you are interested in more information about Pasiphae, you can go to this white paper, which is on the archive. If you are interested to have more details about the instruments and southern instruments, most generally, you can go to those papers that are online and accessible on the archive as well. And if you have questions about more scientific, astrophysically speaking, scientific questions, then we have those this suite of paper. Of course, if you have direct questions, I will be likely to, well, I would be happy to answer them. And if you have no question right now, I will stay available through the Slack by email if you want. Thank you.